All right. So today we're going to be talking about connecting rate of change and slope. So I'd like to start out, does anybody have any good examples of a rate that we see kind of in everyday life?
Car, miles per hour.
Okay, so miles per hour. Any other ideas?
Liters per second.
What was that?
Liters per second.
Meters per second, okay. Anybody else have any ideas? You think of any other rates that you see?
Miles per gallon.
Okay. Yes.
Hot dogs per minute.
Okay, hot dogs per minute. Okay. Oops, okay, I can't write hot dogs. So these are all good examples of rates. And I have a couple here that we can look at as well. So you actually got a couple of the ones that I have prepared, a couple of the examples. So miles per hour is one of the most typical ones that you'll see used in kind of your everyday life. Couple of these, this is the price of gas at Speedway today. This is how fast I can text. I actually timed myself last night. This is the amount of data that my family is allowed to use per month based on our data plan. So what do you guys notice from these rates? What's similar about all of these? Okay, that's really good, yeah. So you have something over something, so you're comparing two things. What's something else that you notice?
Always over 1.
Okay, so traditionally rates are given in terms of something happening based on one of something else. That's good. Anything else? Any other comments? Okay, so I think Shelby hit on the most important one that I wanted to get to. Rates are typically going to be some unit per some other unit. So it's something or two different things, and you're comparing as they're both changing. Independent and dependent variables. Does that sound familiar to you guys? Okay. So in these cases, which one is our, so we have two variables listed here, right? Which one's your dependent and which one's your independent variable? Which one's depending on the other one? Yes, Anne?
Your numerator depends on your denominator.
Right, so our denominator has our independent variable, and our numerator has our dependent variable. So notice that in each of these situations, we have, as Anne said, our independent is in our denominator and our dependent is in our numerator. So we're always comparing some unit that depends on this other unit that is, I guess, more consistent, if you will. Okay. So if we wanted to look at one of these examples specifically, so say our miles per hour, if we wanted to find the rate of change for a car, what information would we need if we weren't given a specific rate, a specific speed? What would we need in order to find that? What pieces of information would we be able to use in order to find a speed of a car?
Distance and time.
Okay. So do we need just one distance and one time? Or do we need more than that?
Use 1 distance.
Okay. So give me an idea of a distance and a time.
26 miles in 27 minutes.
That's super slow.
Okay. So this rate looks a little bit different than our other ones. We could put this as a fraction over 1, but that would require some difficult fractions that we're not going to do right now. So what's another way? So if we were given two different distances and times, so two sets of a distance and a time, how could we use that to find the speed over that period of time in between those two times? Say we were given, let's see, that at 1 hour, a car had traveled 50 miles, and at 3 hours, that same car had now covered 190 miles. How could we find the rate of change between these two different points of the car? Okay.
Final minus initial for both.
Okay. So say that one more time.
Final minus initial.
Okay. So this would be, are you referring to this as our final? And then this is our initial then? Okay. So you could take our final distance and subtract our initial. And in order to have this as rate, we would take our final minus initial and we would compare them by putting them in a fraction. Okay, so what would we get for this then? Okay, what would our numerator be? What's 190 minus 50? 140. Okay. And what would our denominator be? 2 hours, okay. So if we were to reduce this, what would we have? What would our, right. Okay, so just to review, notice what's our independent and our dependent variable in this data point? $50 is our dependent, okay. So that would make this our independent. Right? Okay, so notice that we have our final dependent and we take away our initial dependent, right? So these are both our dependent variables, and this is our independent minus our independent variable. So this gives us a similar setup to what we talked about in these when we had our dependent on top and our independent on bottom. Okay, so this would be our rate of change. So is this realistic? If we have a car trip, does it go the same rate of speed the entire car trip, or does it fluctuate? Right. Okay, so so I have here a table with different time periods over 4 hours of a car trip and the distance that that car has gone at each of those times. So how would we find the rate of change from 1 hour to 2 hours? Okay, can someone tell me what you would need to do?
80 minus 50 over 2 minus
Right, and so this is miles, and this is hours. Okay, so what would our rate of change from 1 hour to 2 hours be? Right. Okay, how about from 3 hours to 4 hours? What would our rate of change be? I'm sorry, what did you say? 4 minus 3, okay. Okay, so what would our rate of change between 3 and 4 be? All right, so notice that our rate of change is changing in this situation. So sometimes when you have rate of change, you can have different scenarios where your rate of change might be changing throughout the time periods that you're given. Okay, so let's look at this same kind of setup in terms of linear equations. So when we have a linear equation, we call our rate of change slope. And we can use what we have just done with rate of change to find a slope when we're given a linear equation. So here are two different representations of the same linear function. Does anybody have an idea of how, based on what we've set up here, so how would we find the slope of this linear function? Okay, so similar to how we did here, where we picked two different distances and two different times, here we can pick 2 points and use that to find the slope. So with all of these, we set it up with our dependent variables on top, our independent variables on bottom, and our final minus our initial in both cases. So if we pick 2 points here, how would we need to set that up in order to find slope? So does somebody want to pick some points and kind of guide me through how you would find slope? Okay. So what would we need to do to find the slope of this? Okay. And then we would have 0 minus -1. So what would our slope be? Okay. So let's generalize this into a bit more of a straightforward formula or rule that we could use to find slope, given any set of points or any different variables with a rate of change or something. What is a rule that we could use so we could always apply this? How would we set that up? So in this we took so you could use either point. Right, so either way you do it, as long as you maintain which one you're picking. So if you were to use this point minus this one and this one minus this one, or start here and work your way down, either way you'll get the same value. So yes, you're right, you would take your y final minus y initial.
All right, so lately we've been working on factoring. And so we've been factoring trinomials. And so I'm going to give you a trinomial, x squared plus 4x plus 1. Can we factor this?
Yes, we can.
We can? How would you do that?
It's that FOIL thing.
That's how we multiply and distribute. So how would we undo that here? Can we undo that here?
We can. I can't tell you how. Well, is there any numbers that add to get to 1 and multiply to get to 4? No. Yep. Wouldn't it be the other way around?
I think Anna's onto something. So recall from our last few lessons that we talked about how this constant term, we need 2 numbers that'll multiply to get our constant term, but add to get our linear term. And so are there 2 numbers that multiply to get 1 and add to get 4? Right, so can we factor this? No. Right, so what are we supposed to do if we set this equal to 0 and we're to solve for x?
Quadratic formula.
You get a little ahead of me, but very beautiful observation. So a very beautiful thing to look at with this is something that gives us the quadratic formula. So I want to take a different approach to look at this. So let's look at area with it. So let's just look at the left-hand side of our equation right here. So if we have something with area x squared, and it's a square, what are the side lengths? Perfect. Okay, and so let's say that we want to create a square. So we want to keep the same shape. So if we do that, it's going to come somewhere out here, but it's going to still be a square, which means that what does that tell us about the side lengths? Okay, perfect. And so we took care of this, check. So what about our 4x? So if we have a rectangle or a square with area 4x, what does that tell us about the side lengths? Right, so that means that one of our side lengths needs to be what was that you said? 2x? And where did you get that? Half of? Yes. So if we want to, let's split this in half then. So if this length right here is x, then what can we put up here to keep this? So if this length is x, then what, if this area needs to be 2x, what does this side length need to be? Right. So we have an area of what here? For this rectangle, 2x, correct. And we're going to do the same thing over here. So the side length down here is going to be, right? Because this is perfect. And so this is, all right, so we have x squared plus 2x plus 2x. And so theoretically, this in sum is going to give us our area. So let's deal with our 1 now. So can someone tell me what the area of this blank spot is? Close.
4.
Yes. Why?
Because the side length of that square would both be the same as the side length, shorter length from the 2 rectangles.
Right. So you're saying that because of this length and this length here, that this area is going to be 2 by 2, or 4. So we have 1 left. So if this is 2 by 2, then this is our last bit, right? So do we have a square? Right. What are we missing? Let me erase this for clarity reasons. 3. Why? Where'd you get the 3 from? Right. So we're missing a 3 to complete this. So in order to complete the square, we're going to need 3 more units. And so let's add our 1, but then let's also add our 3. And because we have to keep this true on both sides of our equation, we're also going to have to do what? Beautiful. So then we can combine like terms. And so we only have 1 x squared unit. And then what would be next? And then equals 3. Okay, now that we've written this, I'll write it up here because you cannot see that really. Okay, so we added our 3 here. So we have a square. What's the area of our square? What was that? Can you tell me how you got that? You're fine. So you're saying that because we have 2 and x over here and 2 and x on this side length, that it'd be 2x squared. Okay, you were very close. So what's happening down here with these side lengths? Right. So when they're being added together, are we going to be multiplying them or are we going to be adding them? Perfect. So looking at it that way, you were close. What would the area of our side be? So what's this length right here? Perfect. And then what's this side length here? Perfect. So then our area is x plus 2 squared. So x plus 2 times x plus 2 x plus 2 quantity squared. So now let's look back at our trinomial that we were trying to factor earlier. Now that we've added that 1 over here, how does this factor? How does it factor? And how did you find that? So think back to what Anne said at the beginning of class. So she mentioned that we want two numbers to multiply to get our constant term and add to get our linear term. So are there two numbers that exist that multiply to get 4 but also add to get 4? 2, right. So then if we set this up the way we normally would factor it, what two numbers would we have? So this simplifies to what does this look like? Right, it looks like the area we just found. So what's different about this from what we started with? So up there, when we set that equal to 0, we couldn't solve for x, right? Because it was not in factorable form. Can we solve for x here? How? How do we get x by itself? Okay, so we'll take the square root of both sides. And what does that leave us with? Missing one more thing. Perfect. So we have plus or minus the square root of 3. And then finally, how do we get x completely by itself? And so these would be our two solutions to our quadratic. So just like before when we would factor it and we would have x plus 2 times x minus 3, and then we would set that equal to 0 to find our solutions. In this case, we can take the square root of both sides and we can find our two solutions here. So these two solutions would be -2 plus the square root of 3 and -2 minus the square root of 3. So this is a process that we call completing the square appropriately. So it takes something that we can use, so we can connect this to geometry or our conceptions of area. And then we are able to complete the square, and then that gives us something that we can actually factor and handle. Are there any questions? Yes. Yes. Does someone want to answer that? Or does someone have a conjecture as to why we can't just take the square root of this? It's illegal. Talk to your neighbor.
All right. Well, good evening, class. My name is Mr. Moss, and today we are going to be talking about, as you may have guessed, operations. And the goal of today's lesson is to figure out which operations come first when we evaluate an expression that has more than one. So the first thing I want you to do is to consider the two sentences that are on the screen. And I want you to tell me what is different about the first one than the second one. What's different? What's the difference between the first sentence and the second sentence? Somebody give me an idea.
The first one is teacher talking, next one is kid.
Okay, so one person said there's commas. So yeah, there are 2 commas in the first one. We have one right after the word Ted and after the word teacher. And she was saying, I hope you guys heard this, that we're not really sure who's talking in the first sentence, right? The second one has a different speaker. Okay, so you said Ted was talking in the first one, is that right? Or did you say the teacher? Teacher was. Okay. Do you think maybe Ted could be speaking in the first sentence as well? No? See, I would think that maybe depending on how we read it, it's kind of hard to interpret who's speaking, is it? It's not really clear. Yeah, exactly. Without quotation marks, it's difficult. Well, in your English class, you've probably learned by now that there is a preferred method to structuring sentences and placing punctuation that helps to interpret what is being said and makes the speaker more clear. Well, in mathematics, we have something very similar to that, and it's a guide that helps us to figure out which operations to perform first. Okay, so the next thing I want you to do is to consider this expression. I'm going to write it here. 5 times 5 plus 5. Somebody evaluate this for me and tell me how you do it.
You would do
Yes.
5 times 5 first, 25.
Okay, so we do this operation first, and that gives us 25. Then what?
Add 5 more, so you get 30.
Then we do our addition. Okay. And she said we result in 30. So we're moving from left to right. That makes sense. What if I were to maybe rearrange the expression to something that's equivalent? Maybe 5 plus 5 times 5. You have to excuse my little lines there. Now we know these are equal because we have 3 5s, so that's the same. We have a multiplication symbol, and we have an addition symbol. So we'd probably move the same direction, right? From left to right. Makes sense. So from left side to right, we see 5 plus 5 first, and that gives us 10. And then we multiply by 5, but wait, that gives us 50. And that's definitely not equal to 30. Someone give me a reason why we have 2 different answers when we solve equivalent expressions. Okay, so she's saying that in the first one we multiplied first, and then we did addition, and in the second one we did it in the reverse order, addition first. I like that, that's reasonable. But how do we know which one is correct then? We don't. Exactly, and that's what I want to talk about with you guys, because this order of operations that I'm going to talk about next is actually the way in which we know which answer is correct. So here's the technical definition here, and I'm going to give you a handout with this later. The order of operations is a collection of rules that defines which procedures or operations to perform first in order to evaluate a given mathematical expression. Now this sounds like it would be pretty helpful, because that would help us figure out which of these answers is correct, right? All right, so the next thing we're going to do is I want you to list off all the operations you think of, and I'm going to write them on the board here, okay? So go ahead and shout them out to me. Obviously, we've already worked with addition and multiplication, but what are the other ones you can think of?
Division.
Okay, so
Subtraction.
subtraction. Anything else you can think of?
Division.
Division, yep, heard that one once.
That one's important.
Sounds like it is important, I would agree.
Parentheses.
Okay, so exponents. And I'm actually going to rewrite parentheses in a little bit of a different way. I'm going to call it grouping symbols. You guys are fast at this, trying to keep up with you. All right, so what do you think is meant by the word grouping symbols? You said parentheses, and that's really one great example. Can anybody think of another example of a grouping symbol? Something that sets something apart? What were you saying? Brackets, yeah, that's a great example. Maybe you've seen something in the form of this squiggly line looking thing. It's also another form of bracket, right? Okay. So anybody have an idea why maybe I ordered the 6 operations in this direction? From 1 to 6, starting with grouping symbols and ending with subtraction?
Number 1 is the most important to do first.
Okay, so maybe order importance. I can see that, but I think multiplication is just as important as addition. So nobody can think of maybe another reason why we might have ordered them in this way, perhaps?
That's the order of operations.
Oh, brilliant deduction. Okay, so this is the order in which we need to perform the operations to make sure we get the correct answer. All right, so the next thing I want you to notice is that the next thing I want you to notice is that when you see our expression with maybe more than one operation, such as what we started with, this order helps you figure out which one to do first, right? That's the whole point of it. I'm going to go ahead and pass something out here for you. And if you would, please take one and pass it around, make sure everybody gets one. You would pass this around and make sure Dr. Singletary and everybody gets one. I know this handout here is kind of going to be your homework. I want you to look over this for next time we meet. But for right now, I just want to address the first section above the line. Now, The first thing we see is grouping symbols that we already mentioned. That's parentheses and brackets. What would you say the next operation that we need to perform, or excuse me, what would you say the next thing we need to do once we've identified our grouping symbols is? Any guesses? Look for exponents. Right. So we've seen our grouping symbols. Maybe we have something like 5 plus 3 minus 1. This is parentheses. So we do what's in the parentheses first, because that's our grouping symbol. It makes sense. And the next thing that we do is we look for exponents. There's none in this one, but if I were to perhaps add something like 2 squared, that would be the next operation to work with, right? Because that's the next thing on the list. So the next step here is kind of interesting because we have multiplication and division. And these are actually going to be performed simultaneously, even though they are 2 different steps in what I've given you. Based upon the relationship between multiplication and division, could anybody maybe offer me a reason why this might be? Somebody give me a reason that they could think of. I want you to think about the relationship between multiplication and division and tell me why you think we might do them at the same time. Yeah. Okay, so they reverse each other, they undo each other. All right. You probably heard this before, but maybe the term inverse operation will jog your memory here. So you already talked about undoing a little bit. I'm going to give you a quick example of what we mean by that. Say we have 2, and we multiply it by number 6. That would give us 12, right? What if we were to take that 12 and then we divided it by 6? We'd get back to our original number, 2. So they undo each other. They're inverse operations. The next 2 steps in our order are addition and subtraction. And just like multiplication and division, they too are inverse operations. You add something to a number and take away the same amount, you get what you started with. And these are the next 2 steps that you're going to look for when you evaluate an expression. Okay, so the next thing I want you to do is I want you to stand up. And I'm actually going to have you do something you might be uncomfortable with, but I think it's a good reminder here. This is kind of a lot to digest, right? It's something that's maybe a lot to remember. So I want you to repeat after me. Give everyone more delicious applesauce.
Give everyone more delicious applesauce.
A couple people were trying to be quiet on me. Let's try it again. Give everyone more delicious applesauce.
Give everyone more delicious applesauce.
Yes, thank you. You can sit down now. I appreciate that. Now, the reason I had you say that phrase is because it's actually really helpful when we think about the order of operation. Notice the first letter of each of those words, give. And that relates to grouping symbols, right? Everyone, that relates to exponents and exponentiation. More, multiplication, delicious, division, apple, addition, and obviously sauce, subtraction. You could also think of it as GEMDAS if that helps you remember a little bit more. Okay, so let's do a quick example here because I believe we have a couple minutes left. Let's try something along the lines of, I'm going to work it over here so you can see better. Let's see, 5 times 3 minus 1. And I'm going to say that is divided by 1 to the 5th power. And then let's just add 10 on for fun at the end. So based upon our order of operations, what is the first thing that we're going to look for in this expression if we evaluate it? Grouping symbols. Do we have any here?
Yes.
Okay, and what are they?
3 minus 1.
Okay, so that's the operation inside the parentheses, right? Inside of our grouping symbols. So that's the first thing we need to work. So 3 minus 1 is? 2. Right. And then if we were going to be really technical, we might just go ahead and write out everything else. And what's the next thing we're going to work for?
Exponents.
Exponents. And do we have one here?
Yes.
Yes, we have 1 to the 5th. So somebody tell me what 1 to the 5th is. 1. Awesome. I chose one that's a little bit simpler, but you might see something more complex like a square or a cube of a different number other than 1, and that would change it. Okay, so that's 1 now. So what's the next operation we need to look for?
Is it supposed to be 5 plus 2?
Thank you for catching that. It does sound a little weird, doesn't it? We missed one. Okay, so what's the next operation set that we look for?
Multiplication and division.
And multiplication and division, right. But we have both. How do we know which one to do first? Left or right? Why do you think it's left or right? Reading order, exactly. Okay, that works too. Just like in the sentences with the word 10, we read from left to right. Well, this is nothing different than a mathematical sentence, so we work the same way, from left to right. So the first operation, 5 times 2, and that gives us what? 10. Okay. And then we have to write everything else out to make sure we're on the same track. Somebody walk me through the next step. 10 divided by 1, and that gives us 10 again. Then we bring down. And the last step, add 10. What do we get?
20.
We get 20. Right. So 10 plus 20 is 20. So this whole expression here, when we evaluate it in the order of operation, will result in an answer of 20. All right, so for homework, I want you to review this sheet, the top half. Remember to give everyone more delicious applesauce, and the next time we meet up, we're going to pick up with this problem on the bottom of the sheet and work through that. So if you want to get a little bit of a sneak peek, that's what we're going to do at the start of next lesson. That's all I have.
Today we're going to be talking about graphing inequalities. So what do you all remember about inequalities? True. Arrow sign? Like this? Right? Okay. And so what is that?
The alligator's hungry.
Right. To which side?
To that side.
Yeah. Okay, so what does this sign mean? Less than. Okay. What does this one mean? Okay, and what if I do this? Gotcha. Okay, so let's do a quick little review, okay? And I want you to graph these inequalities on a real number line, okay? So we have x is greater than or equal to 4, and x is less than 0. So if we're going to graph those on a real number line, you know what I mean when I say real number line? Okay? Okay, so this is a real number line. Got 0 here in the middle. So if I were to graph these expressions or inequalities on that number line, what would it be? What would it look like? I want you to graph them on separate number lines, because if we graph them on the same number line, it means something different that we'll get into later. Okay. Now this one, it's 0 is less than, not equal to. Okay, you graphed it right, but just your signs. Yeah, there you go. Okay. See what you got here. All right, that's good. Perfect. Okay. Chris, how we doing? Good. Okay, seems like everybody has it. So now let's look at, now let's do another little review here. How would I graph these two on a coordinate plane? So we have y equals 4. We have y equals 1/2 x plus 3. So these are lines on a coordinate plane. Okay. Yes. You can do it on the same. Yeah. Yeah, there you go. Okay.
Yep.
Let's think about this one. Yeah, there you go. You got it. Okay, will you put this up on the board for me? Yeah, thank you.
Don't forget this part.
Okay. And will you put these two up on the board for me? Okay. Okay, so I've had a couple people put their answers up on the board. Do you all agree with their answers? Thumbs up if you agree. Good deal. Okay, so now what we're going to look at today is how to graph inequalities. So these are just linear functions, right? These are linear functions. And so today we're going to look at linear inequalities. So let's take a look. Let's not look at the y equals 4. Let's take a look at this line right here. What do you think would change if I changed this, the equal sign, to a greater than or equals to sign? How do you all think that I would graph that? Yes, Chris?
Just there's a solid line and you shade in all the top area.
Shade in all the top area, so like this. By all of the O's that I'm getting, it seems that this makes sense to everybody. Does that make sense? Okay. What questions do you have? Any?
So is the line solid or dotted if it has the equal to sign with it?
I don't know. What do you all think?
It could be that, so it's on that line.
What was that? I'm sorry.
So the greater than or equal to, so it could be equal to that, so it could still be in that line.
Right. So this should be solid, right? Okay. So what happens if I take the equal to part off? It becomes dotted. So we would do this right here. Right? And why do we do that?
Because the numbers on that line would not be represented in your equation.
Inequality.
That one.
Yeah. There you go. Yeah. There you go. Okay. So. Okay. Yes. Question.
So inequalities are not equations?
No, they're not. Because they're not actually equal to each other all the time. Does that make sense?
No.
Okay. They're what we call, I might mess myself up here. They're what we call piecewise functions. Okay, so like, yes.
Okay, yeah.
Does that make sense?
Yes, yeah, I remember the word piecewise.
Okay, so there's a difference between, you can see it graphically, okay? Because if it's just this, if it's equal to, then all of this shaded in stuff gets erased, right? Because we're just looking at this line right here. But if it's greater than or equal to, we're looking at all this stuff that's greater than that line as well as that line. Does that make sense? Okay. So now let's look at a couple of examples here and see if you all remember how we can also manipulate linear inequalities. So let's graph this inequality right here.
Oh, goodness gracious.
Can you flip it?
At some point, yes, I know that happens. I don't know where it happens.
Hold on, Chris.
I know it needs to happen.
Okay. So let's go ahead and do this really quick, okay? So what should I do first? Okay, subtract 4x from both sides. I like that idea. Okay, so I'm going to end up getting. Okay, does everybody agree with that so far?
Yes.
Okay, so now what do I do? Divide by.
Negative.
Right. Okay, so somebody tell me what happens when we divide by. There you go. Okay. Oops. Okay. Now can we graph this? Yes, Chris.
Isn't it -4?
Yes, thank you. You right. Okay, now how would we graph this? Same way we did the other one, right? Except for our y-intercept is -4, right? This is x and y axis. And our slope is what? Up 2 over 1. Up 2 over 1. So our line looks something like this. Okay. So now, where do I shade? And should this be a dotted or a solid line? Right. Okay. Shade above, like this. What questions do you guys have? You good? Okay. So now, oh, yes. Yes, Chris.
What if there are like
Arches? We'll get into that later. Yeah.